Thank you very much to you and all the organizers. I'm having a great time here learning a lot from the discussions and the talks. And I'm returning the favor with an obnoxious title as usual. But so this is going to be most aiming toward work in progress that we're doing with Batul, Gauri, Albert, and Gonzalo, as well as some in progress with Vasu, Ronak, Aingaran, and Gonzalo, as well as with Bruno. And we'll also cover some phenomenology with Oliver. So it's I want to thank all these wonderful collaborators. The theme of this talk is the topology of the universe, and we know very little about this. So if we just think generically, a generic expectation would be that there could be topological features in the universe. The kind I want to focus on today are, in particular, time-like boundaries in the universe. The first two things to say about this is that classically a time-like boundary doesn't warp the space-time at all. It's distinct from any kind of massive particle or massless particle. Quantum mechanically, however, as was discovered in the 70s, there's a kind of boundary layer of UV-sensitive quantum field theory energy, stress energy there, and we'll want to take that into account. This stress energy, as usual in quantum field theory, can either be positive or negative. So in quantum gravity, we also have the extra dimensions, and we're very familiar with the fact that anything realistic, for any realistic models, the extra dimensions are quite rich topologically. And over the years, I've been a broken record stressing the importance of considering the most generic topologies, which are actually quite tractable. They're associated with negative curvature. In any case, whatever you do that's realistic, the extra dimensions have quite rich topology. And so from that point of view also, it seems a bit strange to assume that our four dimensions are pristinely, boring topologically. Instead, again, generically, we'd expect topological features in our four dimensions as well. Now, when it comes to time-like boundaries, the way that plays out is different. A basic phenomenological condition is that we have four-dimensional gravity. So when we think about time-like boundaries that are, say, at codimension 1 internally, things like Hojava-Witten walls or O8 planes, for those who know what those things are, they have a boundary condition that preserves the fluctuating four-dimensional graviton, of course. On the other hand, when we think about time-like boundary topology that might be there in our four dimensions, nothing stops us from considering also a Dirichlet condition, meaning the gravity is frozen on the boundary, but of course in bulk it's still fluctuating. Also in the context of compactifications, we know that it's a very important feature that classical and quantum effects can and do compete with each other. And that'll be an interesting feature that we'll take into account also in our four dimensions in a certain way. Okay, so just to drive this home, the fact that we've discovered the dark energy does not in any way imply that we live in a closed universe. For two very basic reasons. One, we don't see beyond our horizon, so we don't know what features might be out there. But even within our horizon, although cosmology is a very precision science now, it has finite resolution. In particular, you could have a 10 megaparsec boundary out near the last scattering surface, and we would not know. We would be none the wiser. So there's a limit to how much we know now and will ever probably know about this question. What about theoretical consistency? Well, this is a long story, but the executive summary for now is that the kind of boundaries we'll be interested in, including a spherical Dirichlet wall in the universe, is viable according to everything we know from the theoretical point of view, including bottom-up general relativity, where although Dirichlet is not always consistent, it is consistent within a range of in a regime that includes the spherical boundary we'll be interested in. And this has been shown at the linearized level by Nunez et al. And there's a proposed well-posed proof more generally due to Ahn and Anderson on this point. Interestingly, this is a UV-sensitive question, right? We're putting in a time-like boundary. We're thinking about essentially modeling it from the bottom up. It's like an instantaneous reflection. That's a blatantly UV-sensitive thing. And so it's important to only apply low energy GR in the regime it applies, so not take it literally all the way to arbitrarily short scales. We know that string theory amplitudes are soft, and also relevant to the holographic understanding of these types of systems, there's a role for certain double trace deformations, which will explicitly truncate the spectrum. So there will absolutely not be arbitrarily short scales in the problem. There's a lot more to say about all of this. But for now, let me just say that quantum gravity, as we currently understand it, also does not imply that we live in a closed universe. Now, this is a very subtle and interesting question. We're running an entire workshop on it next week at the Simon Center. I think you're welcome to join in, and there's a virtual option as well. Okay, so I won't, because I'm scared of that contraption wherever it is, I'm not going to dwell too much on this. One needs this initial boundary value problem to be well posed. That means you need existence of solutions, and you need them to be unique. So you need initial data within the existing part of the universe to evolve uniquely to the future. Things can go wrong with that. For example, if you look at just a flat wall in flat space-time, you find problems with that. But away from that, those problems explicitly go away if you don't take an infinite angular momentum or momentum limit first. Okay, so that's just a little more on that. Now let's move to semi-classical effective field theory. So again, back in the 70s, people noticed, and it's quite easy to see why, that quantum fields build up stress energy near these boundaries. Again, you don't take that literally all the way to arbitrarily short scales, so we'll cut it off at some UV scale that I'll just call MUV. But what it means is that there's an energy density accumulating at these walls that can build up quite significantly. And interestingly, as has come up in some earlier talks for more formal reasons, it can be negative or positive. Okay, so there's that. Also, again, this kind of competition between quantum and classical, including just one loop quantum stress energy and classical forces, is a feature of any kind of realistic string compactification as well, so in the extra dimensions. Okay, I already said these things. In string theory, things are soft. TT bar type deformations lead to a finite spectrum. And in all these cases, there's no role for arbitrarily short scales. The kind of limits people sometimes take in pure GR of, say, taking a high momentum limit with amplitude going to 0. Any proofs that are based on that sort of limit don't apply, and so that's part of the discussion of the proper form of this initial boundary value problem in quantum gravity. Okay, so the outline of the rest of the talk, the motivational speech is over. It is the following. First, we'll talk about what little we do know about this in the real world. We have not yet done the optimal constraints on this, but we've done some work on it, which I'll share. And then I'll come to the more quantum gravity focused discussion of how we develop holographic models using the benefits of these time-like boundaries. Just as a preview for that, although it might sound in some ways more complicated, it actually makes life much simpler, because you can have this frozen gravity boundary, which makes many things much more like they are in ADS-CFT than otherwise. So I'll review where we got to that in a sort of one-sided setting, and then get to the work in progress on the two-sided version of that. So that's the plan. Okay, so it's not a new idea to check for topology in the universe as much as we can, but nobody actually checked for this type of topology, boundaries. The kind of topology people looked for before would be something like a compact hyperbolic space whose topology just happens to be at our horizon scale. That's kind of a coincidence problem, but with the kind of localized topology I'm talking about here, there's no real coincidence problem. It's a different kind of analysis. So if you look at these things one at a time, it's sort of analogous to lensing, meaning CMB photons that reach us. If you track them back, the ones where the boundary was in the way are coming to us having bounced off the boundary. In effect, the last scattering surface has been deformed. And what you see in the CMB is, as a result, a region in the direction of the boundary where a bunch of larger modes have collapsed to much smaller modes. And one should be able to do some sort of analysis of the constraints on this. We haven't done that yet, but what we have done is looked at another regime where there's a kind of population of these time-like boundaries in the universe, just to see what effect they would have and how easy or not it is for them to be there. And even given that, I'm going to take for just this part of the talk, a scenario where the boundary expands with the universe. It's a fixed co-moving size. That makes them even more easy to see than otherwise. So instead, if we take a fixed proper size, they can hide very, very well. In this kind of regime, and we have to make sure it's consistent with everything else we know, the effect on just the overall evolution of the universe can be interesting. It sits here, again, in the scenario with a fixed co-moving size. In the Friedmann equation, it sits here, meaning it affects things sort of in the recent past, right before the cosmological constant takes over. Okay, so just a sanity check what kinds of parameters would be needed for this to compete with classical expansion of the universe. We estimate that with what the overall energy density would be, with each boundary having this energy coming from the accumulated stress energy of the QFT fields at the boundary. And we compare that to the energy density in the universe, h naught squared m Planck squared, where h naught is the current Hubble, up to some percent. And it's easy to estimate that. And since these boundaries can be much larger than the Planck scale, it's easy for this number to be quite reasonable, to be large enough that there's a homogeneous approximation that is available, while also not just being so huge that it's ridiculously ruled out. Still, one has to check consistency in more detail with basic things that we know or we think we know about the universe, going back into the past. Okay, so yes, please.
Sort of thing like defects, manifolds, blah blah blah, that we normally think is swept out by inflation, and then primarily we have to produce after inflation in some way in order to be around.
Yeah, well, that's part of this story, right? If it's at fixed co-moving size, it's just growing with the universe. So when we track it back to inflation, what we do is we ask, is it under control back there? So these things are shrinking as you go back in the universe, but at fixed co-moving size, they're not lost. So in terms of some origin story for them, they're your guess is as good as mine about what we should assume was there or wasn't there. I'm just making a genericity argument. Okay, so it's given some density today, we track it back into the past. We insist that at the beginning the density was sub-Planckian and the boundaries each were bigger than the Planck length scale. We insist that at the same time there's enough of them that we have this homogeneous approximation. So that's the basic check of control and relevance. And you find if you do that, putting in the prehistory, how far you evolved back depends on details of how high the reheating scale was and so on. And you find that this is not very constraining. In particular, reheating can be anything up to 10 to the 15 GeV, and it's fine. Okay, so the phenomenology job here is basically to make sure it's not in conflict with anything else we know, as I said, and we work in a regime where the primordial linear perturbations are long wavelength compared to this density, while when we get to recombination, the standard model stuff is short scale, and the scattering is not strongly affected by them during recombination. Okay, so I'm going fast here because I'm scared of that contraption, but I think I've hopefully said enough to just explain what the point is, and so one can figure this in to the overall evolution of the universe. Since at late times with, say, negative boundary energy that is available in QFT, it will reduce Hubble and affect correspondingly various distance measures in cosmology, effect of spectrum of modes, and you can analyze that. And the result is some 2 sigma preference for it, and for it to be negative if it were there. Of course, that's not a discovery of anything, could well go away, but it's certainly not the case that it's certainly saying that these things are only very, very weakly constrained in the universe. And interestingly, you get a kind of similar improvement at 2 sigma, not significant improvement from negative curvature. And negative curvature is very, very correlated with rich topology as well. It's the form of, there's a tight connection between, for example, the growth of the fundamental group and negative curvature. And also all of these examples collectively have an enhancement of chaotic dynamics in the early universe. For hyperbolic spaces, the particles spread out. For time-like boundaries, it's like a billiards problem. And the particles also are chaotically mixed. And so people have observed in the past that early universe chaos of this sort can affect how much inflation you need. It's a very interesting kind of case to consider for that reason as well. In any case, we don't know, we'll probably never know what the topology of the universe is unless the constraints really get stronger in a positive way. But again, the point here is don't imagine that the discovery of the CC implies a closed universe. That's very far from the case. And then generically, we would expect topological features to be there, I would say. Okay, so now let me switch to the more aligned stuff that's aligned with this workshop, meaning holography and quantum gravity. And here I'm going to explain the utility of, so far I've made kind of a genericity argument that we should consider this case of rich topology, including time-like boundaries. Now I'm going to explain why it actually helps us with understanding holography. The key point here is that just like for ADS-CFT, but it remains true with a finite boundary, if we say do a fixed intrinsic geometry of the boundary, that means gravity is frozen, and correspondingly, energy is not, and you can have a spectrum of states of different energies. So energy is not constrained to 0. It's meaningful. You can have a multiplicity of states. You can count them, so you have an entropy. It's meaningful. And certain other things, like the first law of thermodynamics, behave in the right way, in the familiar way. So our main result along these lines in the long series of works that I mentioned at the beginning is a prescription for a finite quantum Hamiltonian that we obtain taking this idea and the idea of deforming ADS-CFT to take a very long and elaborate deformation to go from ADS-CFT, which with its infinite spectrum, to a finite theory of time-like-bounded de Sitter space. And the more recent version of that is we realized that it upgrades perfectly well to 4 bulk dimensions. The set of ideas is related to the TT bar deformation, which in itself is a boundary 2-dimensional thing. But we found a very similar deformation in 4 dimensions that underlies that case. So I'll try to focus on that to be definite. And then, as I say, we're going from this to a 2-sided version, trying to understand the physics of that as well. Okay, at the end of the day, this is type 1 for those who like to think in terms of algebra. Type 1 fun. Okay, so Dirichlet boundaries not only are, I'm saying topology is generic, but they give us a simpler understanding of things in the following sense. So whereas a closed universe, as we all know, has the energy constrained to 0, when you have a boundary, you can have a net energy. I guess I'm kind of repeating myself because I said this in words in the last slide, but I find this work of Banahashimi et al. To be extremely important. They noticed that if you consider the time-like bounded case and recognize the energy as the boundary energy, the Brown-York energy, Then what had been very confusing in de Sitter holography, which was the first law of thermodynamics, becomes completely standard. So we have dE equals plus TdS plus bulk excitation. So this is exactly how it looks for black holes. In the past, people were confused because they were doing the closed universe case. This energy was 0, and they had delta E bulk matter equals minus TdS, and there was this whole confusion about the minus sign in the first law. But once you have a time-like boundary, everything is normal in that regard. Okay. Now, so that's one piece of the puzzle. As I say, we have developed an elaborate scheme to combine that with the fact that multiple trace deformations of ADS-CFT change boundary conditions, also with uplifts of ADS to DS, which we have bothered to work out in some cases, and put all that together into a deformation from ADS-CFT, which is the usual thing, to a finite Hamiltonian dual to time-like-bounded DS. To preview the kind of things that go into it before I get into more of the derivation, it's going to involve two pieces. One is a solvable deformation in the same sense that the famous TT bar deformation is solvable. So we'll take an energy spectrum that we know to begin with. We'll grant we know everything about ADS-CFT, which I realize there's a lot we're still learning about it. But anyway, we take the energy spectrum of ADS-CFT, we dress it in a way that's quite analogous to the TT bar deformation. As we'll see, that gives you a finite state theory, a finite spectrum. The count of those states matches what it should in terms of what the top of the spectrum is when you have a finite boundary, either in ADS or DS. And happily, although this will only be a part of the story, this solvable component of this elaborate deformation is something that captures the entropically dominant energy bands. It's a thing that would apply if we just had pure gravity where everything fell into the horizon, a black hole or the cosmic horizon. On the other hand, we need a theory that will reproduce bulk matter details, particles scattering around, and so on. Those things are less entropic, but you know, we need a theory which, at least in principle, reproduces those things. Even though my view is we can just do effective field theory to calculate those things. It's not like we need holography to calculate effective field theory processes. We just want a holographic theory that is consistent with those. And the point of the holographic theory, on the other hand, is to answer questions like this question of the de Sitter entropy. Okay, so that's kind of the philosophy. So we'll have a solvable deformation that by itself is very fun, and you can analyze it explicitly. And then we'll argue that on top of that, we can deform in some way where I tell you at each step of the deformation what else I need to add in order to reproduce bulk details. And that is just a blatant fine tuning, but we'll just argue that we have enough capacity to do that with our finite system. Okay. So the notion of energy that we get when we incorporate these boundaries is the Brown-York energy, same notion of energy we use in ADS-CFT the moment we regulate that. I think people are familiar with this. It's basically a reprocessing of the extrinsic curvature, which fluctuates. Now, I was just stressing that we're going to be particularly interested in a nice piece of this that captures entropically dominant states. What I mean by that are these horizon states, like a black hole DS cosmic horizon. And blackening factor can be written universally in this way, with this parameter eta telling us whether we're in ADS or DS. And you know, the stress energy takes this form that's very simple. It has energy density and pressure in it. And of course, above 2 dimensions, there's a lot more to it, corresponding to bulk gravitons. But for these very simple configurations, this is the form that the stress energy takes, just equilibrium thermodynamics. Okay, so in general, we know that multi-trace deformations change boundary conditions. There's a particular type of deformation that changes the boundary conditions such as to produce a finite Dirichlet wall with everybody having a local boundary condition at that wall. So not just gravity. In 4 dimensions, we have gravitons, which are analogous to matter fields that we also have in 3 dimensions. So I will focus on the gravitational equations, but matter is included, just to be very clear. So at the large n level, it's very simple to derive what deformation is required to do this. It proceeds as follows. So you take one of the Einstein equations, the radial Einstein equation, and write it in terms of the Brown-York stress energy tensor. This is work of Tom Hartman and company, building from earlier work of Herman Villenda and company. And you so plug that into this equation and process it a little bit, recognizing that the trace of the stress energy tensor generates scale transformations, and the deformation that we're talking about has a scale-dependent parameter. It's an irrelevant deformation with dimension-full parameter lambda. And the equation massages into this equation, which is a differential equation describing a deformation of the Hamiltonian by this particular double trace operator at each step of the deformation. As you keep doing the deformation, you're going to generate a complicated multi-trace deformation, but at each step, it's quite simple to write down. One of the things we noticed both in boundary 2 and boundary 3 dimensions now is that when you add a constant to this differential equation, it retains the solvability that the original TT bar deformation of Zalmalochikov and company had. But I want to explain first what the solvable part of this that I'm talking about is in the bulk 4-dimensional case. Okay, but for now, this is the semi-classical expression for what to do to bring in the boundary in ADS-CFT. And also, if you have a boundary, regardless of the sign of the cosmological constant, this expression tells you how to move it around in terms of boundary degrees of freedom, which are include the boundary stress energy tensor. Okay, so the solvable thing is, part of this is first to just focus on these configurations I talked about earlier, where the stress energy tensor, we limit to this very simple form. When you plug that into this deformation, you get a differential equation, which is just the same degree of difficulty as the one of TT par, meaning that you can solve for the effect on the spectrum. You know, you get a differential equation here. You just, everything is energy density or pressure. So it's a differential equation for the energies as you move the dimensionless parameter y around. You can think of the deformation in terms of the dimensionful coupling lambda I introduced earlier, or changing the volume of the space. On the gravity side, it's more natural to think of changing the volume of the space, but it's the same move that you're making in terms of the dimensionless deformation parameter y. Okay, so you get this solvable deformation of the spectrum, and it takes this form with a square root. The square root is similar to what you may have seen for TT bar, where keeping only the real spectrum, and in gravity language, not switching to a Cauchy slice, but staying with time-like boundaries, you reach very naturally a cutoff on the spectrum. So the energies only go up to a finite value, and since the spectrum is discrete, it's a finite quantum system at this point. Okay, so if this, okay, so that you have this, I mentioned an uplift, and continuing only with this solvable deformation for the moment, we take it for a while until such time as the square root in this stress energy formula goes to 0. The dependence on the bulk cosmological constant, this eta, is only sitting there in the square root. And once that goes to 0, you can continue the deformation in a continuous way, having uplifted to the de Sitter version of these equations without losing anything. And what's going on the gravity side is the boundary has come into a black hole horizon. And you know, in the 4 dimensions, if you're near any horizon, you really can't tell whether it's ADS or DS. You're so close to the horizon that the bulk curvature doesn't enter. And that's the gravity side avatar of this fact that the piece of the energy spectrum that would know about de Sitter or anti-de Sitter disappears. Okay, so after that, you add this plus lambda 3. It's still solvable, and you get the spectrum of, you get the Brown-York energy of a time-like boundary in de Sitter space as you continue this deformation. The spectrum is finite, everything is well defined, and the states count here is the horizon area in Planck units or exponential of that. And that's clear from what I said about the black hole first, before we uplift. We have the usual count of states in ADS. When we uplift, we preserve that, and this deformation proceeds energy level by energy level, and the count of states is preserved. So this by itself is not yet taking care of bulk matter, which we'll talk about shortly, but it gives a model that reproduces a function's worth of information about the geometry of time-like bounded de Sitter space, namely the stress energy as a function of the size of the boundary in gravity language. And at the same time, it gives a count of states that very precisely matches the Gibbons-Hawking entropy. Okay, now to augment this in the way that we need to do to take care of the fact that there are matter fields flying around gravitons in 4 dimensions that are not, that once you include those, you go down in the spectrum, you have less entropy, but you want to get those right. And we don't have anything that's elegant to say about that, except to say that we can readily include those effects, the contributions to the double trace deformations that we need to maintain locality of the boundary conditions for all those fields. We can very well add those. Okay, so first there's a step of regulating the whole thing using pure solvable t-squared up at a very, very high scale where quantum gravity affects, where we don't screw with anything that we know in the low energy theory. We just regulate it using a little bit of t-squared solvable. After that, we proceed to add the full t-squared operator that Tom and company instruct us to use down, and we have to add it in the way that the large N analysis says, along with matter fields, double trace operators as well, down to the level where GR applies. Now, GR is not applicable at very short scales. And so with our finite but enormous spectrum, we have ample ability to match the definition of these operators and add it to our Hamiltonian simply by fine-tuning, defining these operators within our energy basis to match those that we know about from GR and EFT when those are valid approximations. And if nothing else, I expect there's some more elegant way to do this, but at least we can argue that we have the capacity to add those things. If we had to fine-tune it at every step, we could do so. And the point of this is not that this is the way to calculate bulk EFT processes. No, effective field theory is good for that. It's just to say that we can match those and not screw up the nice part of this, which is the state count that we get from the solvable part of the deformation, which again captures the most entropic bands of energy levels. Okay, so that's the basic idea. There is an uplift involved. That's really, it's quite complex when we work out these string compactifications, but from this holographic point of view, it's all sub-Planckian stuff. It's just some details. It's part of the matter theory. We can bring that in to the boundary conditions for scalar fields that uplift from ADS to DS and incorporate that in this story I told about the matter part of the spectrum. We're working more on these hyperbolic compactifications, which are very explicit. And that is a lightning review of the one-sided story. Oh, it's right there. Okay, I don't know. So we're starting from that now to try to, okay, this is about to go off. Okay. What does that mean again? Okay. Yeah, we're doing the two-sided thing. If anyone asks about it, I'll say a little bit more. If you want to. Let me say a couple things about this really. Okay. All right.
I did ask you, so it's fine.
Oh, did you? Oh, thank you. Thanks.
Can you spend 2 minutes telling us about this, please?
Yeah, so a natural next move is to consider two of these boundary theories that I just described and try to combine them in a way that will formulate a timelike-bounded patch of de Sitter space that goes beyond just the cosmic horizon patch by itself, which was the band of energies at the top of this spectrum. In general terms, the Hamiltonian should match the sum of the brown-York energies on these two boundaries. One thing you might ask is, isn't there an infinitude of modes up here that you could have, and don't you need way more entropy than the finite theory I just mentioned, or two of them? But we're taking the point of view that if we're going to formulate something that actually has the neck of de Sitter intact, then that's not the case. So if you put too much excitations either in the top or the bottom of the picture, you destroy the neck, and we're just not formulating that case. So there's a nice paper by Steve Giddings and Don Meroff that includes an estimate of how much entropy you can tolerate before you destroy the neck, and our theory has more than that, so it's fine. Okay, so you might want to formulate the thermofield double state. We can, once we have these two Hamiltonian systems, we can formulate this state. Plug in, so one interesting thing is if we plug in the spectrum that I just told you about, which is very top, it's finite, it's very top heavy, it has this huge band of energies at the top and some lower entropy stuff further down. Plugging it into the thermofield double, which has a beta parameter, still gives us a state that's approximately maximally mixed, even though there is this beta in there. So you normalize the state and plug in, and you get something of that character. People have observed recently that indeed there are two notions of temperature and de Sitter, and they coexist peacefully. So there's this beta C, and there's the approximately infinite temperature in the sense of the maximal mixing. Okay, we could think about this microcanonically and try to make what is a unstable saddle instead stable when we think about the partition function. But what we'd like to do is follow the steps of the old two-sided black hole. Let's say we try to make sense of canonical first, and we formulate the thermofield double, as we just said, in the boundary, and then in the bulk we fill in the solution and whatever other configurations we should take into account. We have our own version of the Hawking-Page transition here, where if the bounding cylinder is big enough compared to the beta scale, then the picture is like this, where the solution fills in toward the middle, meaning that the state you're preparing is connected. In the other regime, instead, you get two of what we call the pole patches, where you have this same boundary, but you fill in the other direction. And that dominates, depending on, as usual, the relative size of LC and beta C in this stuff. Okay, now there's been a persistent question and confusion about what is the right calculation of the entanglement entropy in this. And we're going slowly with that because this is one of those, even classically, one of these Euclidean path integral calculation things where you have to worry about what contour and so on. But one thing I want to bring in is that in this de Sitter version, actually, that stuff I mentioned earlier about the way that quantum field theory energy can compete actually arises in this context. So there's a lore that in this kind of setting, we should expect that the RT surface wants to slip off and wrap the boundary. Now, so in some way of doing this, you're saying some cosmic brain wants to shift, slip off the middle and be around the boundary. That is a massively UV sensitive claim. Okay, you're putting this object right near the boundary where there's a huge buildup of quantum stress energy. And in fact, it's hard to get away from the effect of that if you try to move the cosmic brain closer and closer to the boundary. Here's a little estimate of that based on the same kind of effect that I mentioned earlier in the phenomenology part of the talk. So one interesting possibility, although this would take much more to, it's kind of uncomfortably model dependent, and it would take more to really establish one way or the other. But there's a possibility here that there's that kind of quantum field theory effect pushes back and makes the stable thing sit in the middle after all. I'm not, this is still work in progress partly for this reason, but I want to, for now, just say this is a UV sensitive question, interestingly. In De Sitter, everything is not arbitrarily far away from everything else. And above the Hawking-Page transition in particular, the beta circle is really small, and so that's why this is happening. We can avoid this question by working with a boundary that's quite near the horizon. I won't abuse the time, so let me just say, in this context, HKLL, causal wedge, old-fashioned causal wedge reconstruction, goes further, and that's because as we add matter in DS gets taller, so we can reconstruct more causally from the boundaries than would be the case in ADS, where when you add matter, it gets wider, and you have to start talking about complexity and whatever else. We have a way of building in the operator redundancies that appear when the state gets tall. For example, if you take this point here, this phi, it could be reconstructed from the left boundary or from the right boundary, and those cannot be independent operators. They have to, there's an operator redundancy there. The way we incorporate that is we don't just have a product of our two Hamiltonians. That's not it at all. There's constraints that project out what would be inconsistent joinings of what otherwise would be independent product states of the left and right wedges here. So when we impose this constraint, we automatically impose the operator redundancy that needs to be true. So there's that. I'm trying to give you a flavor of the sort of construction we're working on. But again, a nice thing is that HKLL goes much further here. So it's going to be more about that and less about entanglement wedge reconstruction in this context, interestingly. So another thing that can happen is, in fact, the other boundary can be in the causal wedge of a given boundary, and then its own Brown-York energy can be reconstructed from the other boundary in a formula schematically like this, where this K, as before, is some HKLL kernel. So yeah, so that's, okay, there's another approach where we go up to Cauchy slice holography instead of going over. I am not doing this justice here, but this is related to something that Ahmed wrote about black holes getting Cauchy slices from this sort of TT bar plus lambda 2. With these guys, we're looking at it in this way, where we change gears and go from what would have been a time-like boundary actually to a space-like boundary. So, okay, now I'm really at the summary. Thank you, Daniel, again. Let me stop. Sorry.
If you start with two ADS boundaries and apply this deformation process, how is it possible to end up in a situation where there are operators on both sides that don't commute with each other?
Yeah, so once you have this constraint, now you're deforming a system that eventually becomes very different from the ADS CFT version. And once you have this constraint, you find that it's easy for operators to not commute. I didn't go through that, but it's part of the story. Yeah.
Deformation process is not local.
It gives both this operator redundancy I mentioned and that there are non-zero commutators when there should be. So that's a great question, but yeah.
Okay, unfortunately, we have no time for more questions, but let's thank Eva again.